transition metal. So far we have seen about the transition metals, their characteristics, properties, and few of their important compounds and their preparations. Now in today's video, we'll see about the inner transition metals or the F block. Okay. Now F block consists of two series, lanthanides, the 14 elements following lanthanum, and actinides, the 14 elements following the actinum. Okay, so there are two series in inner transition elements or F block, that is the lanthanide series and the actinide series. Now because lanthanum closely resembles the lanthanides, it is usually included in any discussion of the lanthanides for which the general symbol is Ln is often used. Now lanthanum, it closely resembles the lanthanoids. So here in any discussion we will basically use lanthanide as an example or the general thing to represent the lanthanide series. Now it is the abbreviation is Ln. Okay. Similarly, a discussion of actinides include actinum besides the 14 elements consisting the series. So in lanthanides and actinides, all the 14 elements, we will discuss both the series with respect, okay, which are considered to be the representative kind of thing. Now, the lanthanide resembles one another more closely than do the members of the ordinary transition elements in series. Now, in lanthanide series, okay, they resembles very closely with each other. Okay, the features, the properties are very similar for all the molecules, all the elements in the lanthanide series, which is not observed in other ordinary transition elements. Okay, they have only one stable oxidation state and their chemistry provides an excellent opportunity to examine the effect of small changes in size and nuclear charge along a series of otherwise similar elements. Now, here the main thing that we have to keep in mind is that they only have one stable oxidation state. Okay, they have a one very common stable oxidation state, and this inner transition elements, it is an excellent, it gives an excellent opportunity to learn the small changes in the size and nuclear charge and what are the effect that brings with this small change in size and nuclear charge, okay, of the similar elements. Now, the chemistry of actinides is, on the other hand, much more complicated. Lanthanides are simple, but actinides, on the other hand, are much more complicated. So the complication arises partly owing to the occurrence of a wide range of oxidation state in these elements and partly because of their radioactive creates special problems in their study. The two series will be considered separately here. Now, as I told you, lanthanide, it has only one stable oxidation state and it provides excellent opportunity to examine the small changes in the size and nuclear charge and what are the effect or after effect they bring, because all the lanthanide molecules are similar elements with small changes, whereas on the other hand actinides, they are complicated. They are Why they are complicated is basically because of their wide range of oxidation state, and another important thing is because of their radioactivity. Okay, they have a radioactive characteristic due to which the study of these elements become or creates a lot of problems to study these elements as they are radioactive. Now here we will study both this series separately. So let's first start with the lanthanide series. Now the names, symbols, electronic configuration of atomic and some ionic states and the atomic and ionic radii of lanthanum and lanthanoids are given in the table 4.9. Let's go for the table 4.9. So this is the table 4.9. So here these are the atomic number. Okay, atomic number of the lanthanide series, and these are the molecules present in lanthanum. It starts from lanthanum till lutetium. Okay, these are the symbols. It starts with La till Lu. The electronic configuration and their radii. atomic and ionic radii. So this is the atomic radii and this is the ionic radii. AR and IR. Atomic radii, this is ionic radii. Let's see the electronic configuration. Electronic configuration, it may be noted that atoms of these elements have electronic configuration with 6s2 common, but with variable occupancy of 4f level. However, the electronic configuration of all the tripositive ions, the most stable oxidation state of the lanthanides, are of the form 4Fn, where n can be 1 to 14 with increasing atomic number. Here you can see the common is the 6s2. Everywhere you can see 6s2, 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 6s2. So everywhere you can see there is a 6s2. 6s2 is a common electronic configuration, whereas it will start with the filling of 4f1. For lanthanides with a plus 3 oxidation state. So the most common oxidation state for lanthanide series is plus 3. The molecule with plus 3 oxidation state, it will have a readily filling f orbital. So f orbital starts with 0, 1, 2, 3, 4. You can see it is completely filling from 0 to 14. Okay, this is the electronic configuration of the molecules. Now, atomic and ionic sizes. Now, what are the atomic and ionic radius of the lanthanide series? The overall decrease in atomic and ionic radii from lanthanum to lutetium, the lanthanide contraction, is a unique feature in the chemistry of lanthanide. So, here what happens? There is a decrease in atomic and ionic radii from lanthanum to lutetium, that is from La to Lu. There is a decrease in atomic and ionic radii, and this is mainly because of the lanthanide contraction, which is a unique feature of the lanthanide series. Now, it has a far-reaching consequences in the chemistry of the third transition series of the element. I hope I have explained lanthanide contraction while explaining the 3D series or the transition metal elements, that this concept was there. Now, the decrease in the atomic radii, that is derived from the structure of metals, is not quite regular as it is regular in M3 plus ions. So here the decrease in atomic radii is not regular. Okay. As you can see it when there is an M3 plus ions. Okay. The decrease in atomic radii when the molecules are having plus 3 oxidation state. Here all these molecules are having plus 3 oxidation states. So hence their atomic and ionic radii decreases regularly. But when you have something like this is the molecules which show atomic on an oxidation state rather than plus 3 state. Okay, plus 3, some molecules also show plus 4 oxidation state like Ce, Pr and Tb, and some molecules like Sm, U, Tm and Yb. These molecules. Now let's see Ce, Pr and Tb. Ce is cerium, parasodium and terbium. So cerium, parasodium and terbium, they show a plus 4 oxidation state. Here you can see these three show plus 4 oxidation state, but their decreasing atomic size is not regular. Regular as such, plus 3, it shows a regular decrease. Here you can see there is no regular decrease. Now Sm, Eu, Tm and Yb. Now Sm is samarium, Eu is europium. Okay. Tm is thulium and Yb is ytterbium. Okay, all these molecules, samarium, europium, thulium and ytterbium, they show a plus 2 oxidation state. Okay. Now, this contraction is, of course, similar to that observed in an ordinary transition series, and it is attributed to the same cause the imperfect shielding of one electron by another in the same subshell. Now, what is lengthened contraction? Lengthened contraction is basically the imperfect shielding of one electron by another in the same subshell. When the electrons present in the same subshell are not properly shielded, then those molecules are pulled towards the nucleus where the size will decrease. So, however, the shielding of 4f electrons by another is less than 1d electrons by another with the increase in the nuclear charge along the series. Now, 4f electrons, okay, the shielding on 4f electrons is less compared to the d electrons because 3d comes first, then 4f, right? Or 4d for that matter. So 4f electrons are less shielded than d electrons. Therefore, the size will decrease further as the nuclear charge will increase. Now, there is fairly regular decrease in the size with increasing atomic number. That's why there is a decrease in size with increasing atomic number. As the electrons keep on increasing, the nuclear charge will increase, which will pull all the electrons towards it. Now, the cumulative effect of the contraction of lanthanide series is known as lanthanide contraction. When you add all the effects of the lanthanide, uh, all the effects of the contractions of lanthanide series, it is known as lanthanide contraction, which causes the radii of the members of the third transition series to be very similar to those of the corresponding members of the second series. So, what is the effect of this series or this contraction is it will show a very close or similar size similar radius of the members of third transition series with the second series. Okay. Now, the almost identical radii of zirconium and hafnium are consequences of the lanthanide contraction. Now, zirconium and hafnium both have a similar radii. One is 160 pm and the other one is 159. Just 1 pm ka difference, which is very close. Now, this is the consequences of lanthanide contraction. This is like the sizes are very close because of lanthanide contraction. Okay, which the result of this lanthanide contraction making the size so close to one another, it makes or it creates lot of difficulty to separate them. Okay, they face lot of difficulty separation of zirconium and hafnium because they have a similar size. Now next is the oxidation state. As I told you, lanthanide series they have a +3 ka common oxidation state. Now lanthanides, okay, the compounds are predominant species. La2 and Ln3 they are predominant species. Occasionally, +2 and +4 ions in solution or in solid compounds are also obtained. Now, you can get an oxidation state of +2 and +4 in solid solution. Okay, you can obtain +2 and +4 oxidation state also. This irregularity as in ionization enthalpies arises mainly from the extra stability of the empty or half-filled or filled F shells. Now, why you can get this +2 and +4 oxidation state or this irregularity is mainly because of their extra stability. Okay, this extra stability of the empty orbitals or the half-filled or completely filled F shells. Okay, mainly because of these three reasons, you can get a +2 and +4 oxidation states. Now, cerium is favored by its noble gas configuration. Now, cerium has a noble gas configuration, but it is strong oxidant reverting to the common +3 state. So, cerium +4, it shows a noble gas configuration, but it is a strong oxidizing agent as it can be converted to Ce+3, which is its common oxidation state. The Ce can oxidize water. Okay, because it has a plus 1.74V, which which suggests that it can oxidize water. However, the reaction rate is very slow. It can oxidize water, but the reaction rate, it is very slow. Okay. Now, so in common, you have to remember in this part is that lanthanide series, it has a common oxidation of plus 3. Okay, the common oxidation for lanthanide series is plus 3. Besides plus 3, you can also get plus 2 and plus 4 oxidation state. Not more than plus 4 oxidation state is same. Now, why you get plus 2 and plus 4 oxidation state? It is basically because of the empty orbitals or half or fully filled f orbitals. Because of these reasons, you can get a plus 2 or plus 4 oxidation state. Now, general characteristics of lanthanide series. All the lanthanides are silvery white soft metals and tarnish rapidly in air. Now, lanthanides, they are silvery white soft metals. Okay, they are soft metal with a silvery white color, and they can be tarnished or they can be stained by uh, a rapidly passing air. Okay, they can be tarnished by rapidly they can tarnish rapidly in air. They can get a stain on them in the air. Okay, the hardness increases with increasing atomic number. So as you go down the series, okay, as you go along the series, the hardness increases with the increase in atomic number. Now, samarium, it is a steel which is hard. Okay, samarium being a steel is hard. Their melting point ranges from 1000 to 1200 Kelvin, but samarium melts at 1623 Kelvin. Okay, that's why samarium is very hard. Okay, usually the melting point of lanthanides is 1000 to 1200 Kelvin, but samarium, it melts at 1623 Kelvin, which is higher than the original melting point of the lanthanide series. That's why samarium is considered to be a harder metal. Now, they have a typical metallic structure and are good conductors of heat and electricity. Again, they are they show a typical metallic characteristics, hence they are good conductors of heat and electricity. Now, density and other properties change smoothly except for europium and ytterbium and occasionally for samarium and thulium. Okay, so their density and other properties, they change smoothly, okay, except for these four molecules. Mainly trivalent lanthanide ions are colored both in the solid state and in the aqueous state. So since you know ki lanthanides, they follow a common oxidation state of plus 3, that is a trivalent lanthanide ion. This molecules shows color. Okay, color in both the state, in solid state as well as in the aqueous solution. Now, color of these ions may be attributed to the presence of F electrons. Now, since because of their trivalent ions, they show colors. Now, this colors is basically because of the presence of F electrons or F block electrons. Neither La3 plus nor Lu3 plus ions show any color, but the rest do. So, here also there is an exception. Lanthanum, that is La3 plus, and lutetium, that is Lu3 plus. Both of them doesn't show color. So except these two molecules, all the other elements, they show color. Ionization enthalpy of lanthanides are around 600 kilojoules. So the first electron from the lanthanide series, it can be removed with an energy of about 600 kilojoules per mole. Okay, you have to apply this much of energy to remove one electron from the lanthanide series. Now, a detailed discussion of variation of the third ionization enthalpies indicate that the exchange enthalpy consideration as in 3D orbitals of the first transition series. So here a detailed discussion of the variation of the third ionization enthalpy indicates that the enthalpy concentrations appear to impart a certain degree of stability to empty. Now, here also again the for second also there is an increase in the energy, but as you come to third, the energy decreases mainly because by removing that third electron, the molecule can attain its stability by stability to empty. Okay, so um, there can be changes in the ionization enthalpy as you go further. Now, this indicated from the abnormally low value of the third ionization enthalpy of lanthanum, gallium, gallo gadolinium, and lutetium. Now, this was explained by using these three elements as they showed their third ionization enthalpy to be considerably less than first and second. Now, in their chemical behavior in general, the earlier members of the series are quite reactive, similar to calcium, but with increasing atomic number, they behave more like aluminium. So here you can compare their reactivity. The molecules, the early members, okay, from lanthanum to the early 2 to 3, 4 members, they show a characteristic similar to calcium. They chemically react like how calcium reacts. But as you go in with the increasing atomic number, okay, they start behaving like aluminium, more like aluminium. Okay. These metals, they combine with hydrogen when they are gently heated in the gas. Okay. Otherwise, the hydrogen cannot be combined with those molecules. Now, these are chemical reactions of lanthanoids. Okay, how lanthanoids can be chemically reacted. Carbides, carbides that means lanthan, Ln3C, Ln2C3, Lnc2 are formed when the metals are heated with carbon. So, metal hydrides are formed when heated with hydrogen. Metal carbides or lanthanum carbides are formed when they are heated with carbon. Okay. They liberate hydrogen from dilute acids and burn in halogens to form halides. Now, these lanthanides, okay, they liberate hydrogen from dilute acid and burn the halogens to form halides. Okay, here you can see halogens. Okay, halides. With halogens, they form halides. Are the reactions, and they are explained here. Now they form oxides, that is M2O3, and hydroxide MOH3. The hydroxides are definite compounds, not just hydrated oxides. They are basic like alkaline earth metal oxides and hydroxides. Okay. Now they also form oxides and hydroxides. They are similar to alkaline earth metals forming oxides and hydroxides. Okay, they're not just a simple hydrated oxides, but they are similar to the alkaline earth metal ka oxides and hydroxides. Now the best single use of the lanthanoid is for the production of alloy steels. Now lanthanides they can use for the production of alloy steels for plates and pipes. So a well-known alloy is metal, which consists of a lanthanoid or lanthanoid metal. Okay, so lanthanides for the production of alloy steels and plates and pipes. Now well-known alloy is metal, which consists of lanthanoid metal, okay, 95%, and iron up to 5%, and a traces of sulfur, carbon, calcium, and aluminium. Now there are traces of these four metals along with 5%, almost approximate 5% of iron and 95% of lanthanoid metals. Now a good deal of mish metal is used in Mg based alloy to produce bullets. Now where this mish metal is used in is in the production of bullets. It can be used for bullets, shells, and lighter flints by combining it with Mg based alloy. Okay, magnesium based alloys. Now, mixed oxides of lanthanoids are employed as catalyst. So, mixed oxides of lanthanoids that can be used as catalyst in petroleum cracking. some individual lanthanide oxides. Now here, for petroleum cracking, mixed oxides ka catalyst is used. But some individual lanthanide oxides are used as a phosphors in television screen. Phosphors means the phosphorescent or the fluorescent surface. Okay, fluorescing surface on the television screen. Okay, on which the rays are striking and they are reflected to your screen. So they can be used as a fluorescent surface, some lanthanide oxides. So in today's video, we have seen about the lanthanides, their properties, characteristics, and oxidation states. So in our next video, we will see about the actinides. So thank you for watching my video. Please do like, share, and subscribe to our channel.